We have John Kallaugher, who's going to tell us about advantage for a streaming problem, or a natural streaming problem.
Hi, so yes, I'm going to tell you about a quantum advantage for a natural streaming problem. And I want to lead off by just quickly saying what exactly it is that I mean by a streaming problem. So streaming algorithms are this family of algorithms for very large graphs, by which you should understand graphs that are much too large to fit in main memory, that appear one piece at a time. So you start with like an empty data set. I said graphs, they don't have to be graphs, forget that I said graphs. You start with an empty data set and you build it up as a stream of small updates. So examples are things like, imagine that you have a router, it has like a tiny memory and you're seeing this huge flood of network traffic and you want to learn some, like traffic statistics of it. Or imagine I give you, say, the friendship graph of some very large social network as a sequence of events of the form, Alice is friends with Bob, Bob is friends with Charlie, and so on and so on, and you want to approximately learn some function of this graph. So there's a lot of things that you could care about with these algorithms, but in the theoretical study of them, we're primarily interested in space complexity. So what is the smallest number of bits that your algorithm could have and still approximate some function with, say, probability 2/3 over the stream. And like lots of models of computation that are studied, this has a very natural quantum analog, which is, instead of maintaining some string of classical bits, you're allowed to maintain a quantum state. Every time you see an update, you will apply some quantum channel to your state based on the update that you saw. And then the question is, what is the smallest number of qubits that I can let my quantum streaming algorithm have and still approximate this function with, say, with 2/3 probability. Now, since the start of the study of these algorithms, it's been known that at least sometimes the answer can be exponentially fewer. But this original result was for what you could think of as like a quote unquote contrived problem, like a problem that was created to prove this exponential separation. Now, later it was shown that for like a very natural problem, the moment estimation problem, you can get these quantum advantages, but these advantages only arise when you have many, many passes over your data. And so we might want to know what might happen in the more common stream model where you only have one or like only a constant number of passes over your data. So what I'm going to tell you about is a problem that one of the best studied problems in classical streaming, and how you can get a quantum advantage for it using only a single pass over your input. And before I tell you what this problem is, I want to step back and ask just at a very high level what it is that we're looking for here when we look for this kind of advantage. So we're looking for two things, basically. We want a problem that is classically hard, and we want it to be classically hard in a way that does not apply to quantum algorithms. And then we want to go and we want to find a quantum advantage, a quantum algorithm that realizes this potential advantage for that problem. And as it happens, we actually already have a good candidate problem that satisfies the first of these two criteria. And that is the problem of counting triangles in graph streams. So this problem, it turns out, has a lower bound that is derived from a reduction from the Boolean hidden matching problem in one-way communication complexity. I am not going to talk about this problem here. There's the one thing that you'll need to know about it for the purposes of this talk is that it is a problem that was originally created to show exponential separations between quantum and classical complexity. And so the lower bounds from it naturally do not apply to any of these quantum streaming algorithms. And so in the rest of this talk, I'm going to tell you about how we achieve that second bullet point from the last slide and find an algorithm that beats this classical lower bound. But before I go and tell you about that, I should probably tell you what the triangle counting problem that we're going to be looking at actually is. So this is a graph streaming problem, meaning that you're getting this very large graph as a stream of edges in some adversarially chosen order. And your goal is to, at the end of the stream, report approximately how many triangles there are in the graph that all of these edges form. Now, it's probably unsurprising and quite easy to show, and like fairly easy to show, that if you're just trying to say like distinguish between 1 and 0 triangles, that you can't really do any better than storing the entire graph. It turns out that that even if I guarantee that a graph has like omega of m triangles in it, where m is the number of edges in the graph, you still actually wouldn't be able to do anything better than storing the entire graph in general. So you need a bit of extra parameterization. All of these results tend to be like cited in terms of their parameters. But for ease of explication in this talk, I'm going to be assuming for the rest of the talk, we're in a graph that has theta m edges, theta m triangles, and those triangles will all be edge disjoint. And at the very end of the talk, I will briefly mention what this result looks like if you generalize those parameters. So that's our problem. And we want to find now a quantum algorithm that beats this known classical lower bound for it. So a natural place to start looking is at the graph, the instance that is known to be hard for classical algorithms, the one that you get by reducing from the Boolean hidden matching problem. And so what this instance looks like is the following. That slide was accidentally duplicated. Anyway, so you have a star, you have an m star, and that's given to you first in the stream. And then we give you a stream of disjoint edges, a matching, that may or may not complete those vertices incident to that high degree star vertex into triangles. And so you want to estimate how many triangles there are completed. Now, classically, if you wanted to do this, you can get some intuition for how hard this should be, what the correct hardness for this should be by just imagining what would happen if you were just only going to keep some edges from that first star and then check them against the matching edges to see if they completed triangles. In that case, each of these triangles, if you kept k edges, you'd have about a k over m all squared chance of getting any one of them. So to even sample one of the triangles, which is more or less how difficult it is to count them, you would need k to be about root m. Because we're assuming that there are theta m triangles. It turns out this is actually pretty much tight. What the reduction from Boolean hidden matching tells you is that up to a log factor, you really can't do any better even if you can store arbitrary classical state. So that's the instance that we're going to be trying to do well, and we want to do better in particular than this root m classical lower bound. And to start with, we're going to make things as easy for ourselves as possible. We're just going to we're not even going to think about getting this in the stream. We're going to think about a communication game version of this. So we have two players. Alice is going to have that star. Bob is going to have the matching. Alice wants to send Bob the shortest message possible that will allow him to determine approximately how many triangles they have together. And so the quantum message that we're going to have Alice send, and this is kind of inspired by the Boolean hidden matching protocol, is she'll just send a uniform superposition over the vertices of that big star. That's going to take her log m qubits to send because it's a superposition over theta m entities. He's going to measure it using a basis. He's going to take his matching of every edge VW. He is going to add two elements to his basis. I'm going to neglect to say the 1/√2 every time I say this. So he's going to add V plus W and V minus W for each edge V minus W in his matching, and then he'll arbitrarily complete it to a basis of the whole state. And he's just going to measure that superposition using that basis. Why is this useful? Well, we're going to define a random variable x, which will just be 1 if he gets one of those V plus W basis elements, -1 if he gets a V minus W basis element, and 0 otherwise. And I'm going to claim that the expectation of this random variable x is proportional to t. Why is this? Well, for every triangle UVW in the input, so we're using U to name that central vertex of the star, there will be a 2/n chance of getting the basis element V plus W, just because that's its dot product with the state, and a 0 chance of getting V minus W, because it will have 0 dot product with the state. And then for any other situation with regards to VW, both basis element vectors will be, both V plus W and V minus W will be equally likely. Either one of V and W is present, so they both arrive with probability to m/2, or neither is present and they're both guaranteed not to arise in your measurement. So that tells you that we have the right expectation, and because this variable takes values in plus, -1 and 0, it trivially has constant variance. So you can just repeat m²/t² times and take the average, and that will let you get an estimate of t. Since we're assuming t is omega of m, that's a log m qubit protocol. So for this very narrow communication game, we can get an exponential advantage over the best possible classical protocol. But what we want is a general streaming algorithm for counting triangles. So the remainder of this talk is going to be us building this up to a full streaming algorithm, which will require, first, we're going to generalize Alice's input from just being a star to being anything. We're going to generalize Bob's input. And then once we have a protocol for the general version of this game, where both players have a graph and we're just asking how many triangles are there in their intersection, then we're going to figure out how to actually implement this protocol in the stream. So starting with step 1, let's generalize Alice's input. So previously Alice had a star, and she was sending Bob this uniform superposition over the neighbors of her star. What we're going to do instead now is we're just going to have her send a superposition over the neighborhood of every one of her vertices, which is then going to be equivalent to just sending a superposition over each of her edges, where just each edge arrives twice, once as V being a neighbor of U, once as U being a neighbor of V. And so when Bob gets this, he is going to similarly extend the basis he uses. Instead of saying for every edge VW in his matching, he measures with V plus W and V minus W, he's going to add 2n basis elements, where n is the number of vertices in the graph, UV plus UW, UV minus UW for every vertex U. And this will give us basically exactly the same properties we were getting when Alice just had a star. Each triangle is going to contribute θ1/m to the expectation, repeat m²/t² times and take the average. So the Alice part of this generalizes quite easily. But what's going to be slightly harder is generalizing Bob's input. So recall that previously Bob had a matching. But now we ask, what happens if Bob doesn't have a matching? In fact, suppose that he even has 2 edges that just share the same vertex. Well, now we're already in a bit of trouble, because our protocol told us that we wanted Bob to measure with U plus V and V plus W in his basis. But those are not orthogonal vectors, so we can't construct an orthonormal basis that contains both of those elements. So we're going to have to, we're going to have to handle this somehow. And we can start by thinking about what we do if we were just in like that kind of almost not a matching case. Like he had like a low degree graph with max degree D. What he could do then is he could subsample the edges of his graph. And so he only adds each one to the basis with probability 1/d. That would make his graph like almost a matching. And then like maybe he has like a small number of leftover vertices which have higher degree, but then he could just delete those without like getting rid of that many triangles in the graph without damaging the accuracy of his estimate that much. So doing this basically is going to lose him like a factor of D in the expectation of his estimator, because each triangle will only contribute to the expectation with probability 1/d. That means that he needs D squared times as many repeats to get like a good accuracy estimator. And that's fine if D is small, but in general, Bob's maximum degree could be as large as he wanted. So that still doesn't quite solve our problem. So we have to think about like how much damage can high degree vertices do to the accuracy of our estimator. Say Bob just threw away all vertices with a degree above some constant, what would happen? Well, to understand that, we're going to start actually by rolling back the clock a bit and considering what happens when we're in our original hard case, Alice just has a star, but now we've generalized Bob's input. So in this case, I claim that if Bob just deleted all of his highest degree vertices, that actually couldn't hurt his estimator very much. And the reason for that is because in this case, all of the potential triangles are formed by wedges going through this one like high degree vertex Alice has, and they're all edge disjoint. No two of them can actually touch the same high degree vertex that Bob has. So if he, for instance, deleted all of his vertices with degree at least 100, then at most like an m/100 fraction of the at most m/100 triangles could be deleted from the graph. So in this case, we're actually fine. Bob can Bob can choose some threshold, delete all vertices above that threshold, be fine. But in general, clearly this isn't the case. So for instance, so it is possible for Alice to have lots and lots of potential triangles, lots and lots of wedges, which all touch the same high degree vertex that Bob has. But the useful thing for us here is that in order for this to happen, those wedges, those potential triangles, all have to be split among many, many different vertices. And it turns out that this is exactly the case in which it is classically easy to count triangles. So for instance, if Alice has just all of these disjoint wedges, she could just subsample those vertices U0 through U3, and then like each vertex she samples, just keep the two edges that come off that. And so the situation we end up getting is that the triangles that are hardest to count for the quantum estimator are the easiest to count for a classical estimator. And so what we can do is we can interpolate between a quantum and a classical estimator, and thereby we end up getting an m⁵ qubit algorithm, where this m⁵ comes from triangles that are kind of an intermediate difficulty for both quantum and classical estimators. So that gives us our quantum advantage for communication. And so the very last thing that we need to do is we need to actually make a streaming out. We need to actually work out how to implement this communication protocol in the stream. So you can think of this as having two components, right? Like you've got like Alice's part of the protocol, which is constructing the superposition, Bob's part, which is doing the measurement. Alice's part turns out to be like pretty straightforward to do. You have, in order to construct the superposition in the stream, what she can do is she can start with, well, I say she, it's now just the algorithm. What the algorithm can do is that it has starts with 2m dummy variables, and then each time you see an edge UV, you swap out two of those dummy variables for UV and VU. You like maintain a counter as you pass through the stream to tell you which ones to swap out next. So that works nicely, but we can't just maintain the superposition and then measure it at the end of the stream, because just knowing what measurement to perform at the end would require like storing too much information. So we're going to need to find a way to perform the measurement in the stream as well. And so we're going to have to do it essentially one edge at a time. So how's this going to work? Well, what we're going to do is, when you see an edge VW, and remember, because we were doing the subsampling thing, we're going to be only using each edge to measure with probability P, where P will be, I'll explain it in a bit what like P means. So for each edge VW, if you choose to measure with it, you will construct 3 projectors, like a plus projector, a minus projector, and an everything else projector. The plus projector is onto UV plus UW for every vertex U. Minus is onto UV minus W for every vertex in U. P0 is onto everything else. And then, we'll measure with these 3 projectors. If we get the plus or the minus, we will terminate and report either plus or minus 1. Otherwise, we just keep on going. And if we keep on going, that means that we've now projected onto P0, because P0 was the result we got. Which means that in effect, whenever we measure, if we don't end our algorithm, we have deleted every edge incident to V or W from the superposition. So what that means is that for every triangle UVW, if you measure with VW, for every triangle UVW where both of the edges UV and UW arrive before VW, you have like a 1/m chance of getting P+, provided that none of the edges incident to V or W were like removed from the superposition by another measurement. There was no like intervening edge incident to V or W that like was measured with and killed them. So what that tells you is that for each triangle UVW, you can characterize its contribution to this estimator as P times 1 minus P to this intervening degree quantity, where the intervening degree quantity measures those number of edges incident to V and W that could have removed the triangle from your superposition. You'll have a probability P of actually measuring with VW, and then like a 1 minus P to this intervening degree thing of not measuring with any of the other edges. And so basically the triangles where that intervening degree quantity are the ones that cause trouble for the quantum estimator. And by essentially the same argument that we were discussing with the communication version, those triangles with high intervening degree can't be set up in a way that makes them hard to measure classically. Or to remove the double negative, they're easy to find classically. So what we can do is we can run a second classical estimator that estimates 1 minus P to the intervening degree for every triangle in the graph. And then we have these 2 estimators that measure these 2 things. And so we basically just have to set P in a way that minimizes the sum of the errors of those 2 estimators. And that gives you kind of like a final streaming version of this protocol. So that is, all the steps that we needed to get to a streaming algorithm. So just, I guess, finally, as promised, I will present the upper bound that you get in full generality. I'm not going to read out all of those terms, but suffice to say that when you set the parameters in the regime we've been discussing, where theta m triangles delta equal to 1, then you get this like m to the 2/5 versus root m separation, which is the largest separation you get with this algorithm. Now, the one thing I want to note about this is that the best known lower bound for quantum basically disappears. I say basically disappears. You get like a log m factor still when you're in this parameter setting. So it's still possible that you could get as large as an exponential separation between quantum and classical for this problem, or alternatively that there are some other there's some other like quantum lower bound techniques that give you some lower bound intermediate between log m and m to the 2/5. And that is all that I have to say about quantum triangle counting. The one last thing I want to say is that if you are interested in any of these quantum algorithms things and are a grad student about to graduate, we are also hiring a postdoc, no US citizenship required. But yeah, thank you very much for listening.
Thanks for the very nice talk. Do we have questions?
Do you have any other candidates for streaming problems that maybe satisfy some of the criteria you have, but we don't have algorithms for yet?
So like as in ones where there are, I know there are, so I don't have a good example off the top of my head. The Boolean hidden matching problem and its like cousin, the Boolean hidden hypermatching problem, have been used like a fair amount for lower bounds for streaming algorithms. Yeah, unfortunately, I don't have a good problem I can name off the top of my head, but those are both things where you might hope to get. Those are examples of things where you might hope to get advantages.
You could choose.
I think you had your hand up first.
So for the streaming algorithm you described, we're building up the state by adding edges to it, but then we're also using some edges to measure. I didn't quite get, like, do we add and measure up the same edges, or do we how do we choose between what we do? Yeah,
you add, well, strictly speaking, it doesn't matter whether you add then measure, because the edge the things that you add to the superposition are orthogonal to the edges you would measure with for the same edge, because like you would add VW and you would measure with things that like supported on UV and UW for other. I guess if you added, okay, so you could add, I guess, so depending, you could do it either way, I guess is the answer. Like if you do the measurement first, you have to make sure to not include V or W in the vertices. You have to not include U or W in the like set of vertices that you construct the measurement with. But yeah, either way will work.
Actually, so thinking back to the definition of the problem that you're solving, so it's defined in terms of this quantity T, and so you get a separation depending on what T is. Does it somehow make sense to think of the problem of computing the number of triangles up to a certain additive precision, and then getting rid of the promise now as promise on T, or this dependency on the complexity of T? Because it looked like for the Boolean matching version of it, you get a quantum bound which is like the expectation is like T over M or something, so you can compute the number of triangles up to additive error of like order M, right?
Yeah, so this, so in terms of T, I think you can just straightforwardly convert this into an additive approximation in terms of T. So stating like this is like kind of the convention in like these streaming things is often more just to state the state in terms of the parameters. But yeah, I think you can, for this and for all the triangle counting algorithms I know of, you could change the you could state it as an additive approximation in terms of T, but what you couldn't do is get rid of that delta E, for instance, from the bound. So delta E is like this bound on like what is the triangle heaviest edge in the graph. And you do need, that said, I mean, you could, I guess, like add delta E into the approximation. So yes, I think you can in general, I don't want to make a too strong a statement, but I think you can generally like convert it to like an additive approximation in terms of all of the parameters if you want.
In some sense, it would be nice to have an algorithm where you somehow don't have to assume something about the answer before you run the algorithm in the first place.
Mm-hmm. Yeah, and like all of these lower bounds certainly are for like just distinguishing between no triangles and like lots of triangles. But yeah, I think it's more of a matter of like convention. I mean, for instance, actually one thing you could do, so one thing you could even generically do to like convert between them is say something like I will also have like a fixed like T triangle graph that like I insert, and then I guarantee that my graph has like, at least like T triangles, and then so then if I get like an epsilon T error, then that would, I think, actually generically convert it into an additive error version of it.
I don't understand the theorem because like it says that m is 885, but then in the classical it's just m linear. Isn't the classical better than the quantum? Like,
well, it's because so T is to the 6/5, and there is no the point. So you're right if, for instance, like T was like 1. But so this doesn't dominate the classical one for every possible parameter configuration. Although you could obviously just run both in parallel if you wanted to do that. But for when T is larger, because you have m to the 8/5 t to the 6/5 times delta e to the 4/5 as opposed to m delta e over t, then that m over root t. So the answer is that, like, yeah, so in this parameter regime, that like classical thing works out worse. And yes, but yes, you're right that there are parts of the parameter space in which the classical algorithm will be better.
I just wanted to ask if there have been any experimental realizations of this algorithm or similar algorithms, and if not, what would you imagine to be the limiting factors?
So for classical triangle counting, there's lots of experimental realizations of it. For like the quantum version of this, I mean, I guess the obvious limiting factor is that m to the 2/5 versus root m is only, that's like an m to the 1/10 difference. So if you want that to be as large as 10, you need at least m to be at least 10 to the 10, which is just a phenomenal number of qubits. So like the actual, in terms of like what are the constant factors on this are actually like not bad at all. But yeah, the difference, the power of the separation is, I think, just not, it's just small enough that you need like very large instances before it becomes substantial.
Some of the, I know streaming algorithms is maybe focused on space complexity. Do you know what the kind of gate complexity is where you're trying to build?
So the the operation that you're performing to measure the superposition, to maintain the superposition is
Hello.
I can hear the talk at the
the operations you're performing to measure the superposition are just like these two swaps, and then in order to perform the measurement, that I guess if you did that naively, that's like you are having to construct these like 2n basis elements for each measurement. So without claiming more expertise in gate complexity than I have, I think it's quite bad.
Okay. I think we're already 10 minutes past the session time. So let's thank the speaker again. Now it's the investor session, and it's where we have lunch.